Hey, welcome to your first lesson in the first training on Low-Level Academy, Zero to Hero C Programmer. Now, what is this course about? This course is going to be, as the name implies, a Zero to Hero course that takes a beginner programmer with no knowledge in C to a master C programmer. Now, you're probably wondering, why would I take this course instead of the other hundreds of courses that are on YouTube? I've been writing in C for over 15 years at this point, so I have experience and I love to teach. But also, I find a lot of the courses online that already exist in C don't do project-based learning. It's kind of, you write some toy code, you write a hello world, you use a string here, you use a heap there, but none of the training is holistic, where you actually build a thing. And that's where I find a lot of the experience comes from that makes you a good programmer. Coming up with an idea, figuring out how to design that idea, and then writing that idea in code. That design process creates problems that exposes you to issues that make you a better programmer. Now, the project we're going to be doing in this course is fairly simple, but it teaches the fundamentals of the C programming language. We are going to do a file-based database that uses structures and file input and output to store some information of variable length to the disk. And then in later courses on this platform, we'll take that database service that we use as a file service and attach a networking stack to it and a thread-safe thread pool to it, so that combined we have a holistic project that makes use of multiple parts of the POSIX API. And if you don't know what any of that means, that's totally fine. I guarantee you by the end of this course, you will know what that means and be confident in your programming skills. Now, you're probably wondering, is this course for me? Do I have enough experience to take this course? And the answer is most likely yes. If you have done any programming in any language at all, then you're qualified for this course. You don't have to have a huge amount of experience. You actually can have zero experience in C to take this course. If you want to learn how to write C, how to go from being a zero to being a hero at the C programming language, and how to write bigger scalable projects in this language, then this course is for you, and thank you for signing up. We'll see you in the next lesson. Hey guys, welcome back to your next lesson in Zero to Hero C programming. This one has a little less to do with programming itself and more on the pace that you take this course and kind of how to set mini goals and to keep motivation up while you're taking a longer course, learning a new language that may be harder for some people. This is especially important for new programmers, as I think it's really easy to get overwhelmed and maybe even feel like you know a concept early on, but then go to recall that concept later on in a course and be like, oh, I forgot that syntax. So then your entire foundation kind of breaks down. Really, really important that instead of setting this mega goal that, oh, by the end of the month, I'm going to be a master of C programming, instead break that down into mini goals where instead of, trying to master C in this giant gulp, break it down into smaller parts. The mini goal could be, this week, I'm going to understand structures. And then this week, I'm going to understand pointers. Take this course slow, maybe 1 or 2 sections a week. And every time you take a new section, wait a day. And then that next day, write a little bit of code. That will ensure 2 things. 1, that you actually understand the lesson after learning the information directly. And then also 2, that information will get stored into long-term memory so that later on in your life or later on in the course, you can actually recall it. Doing this will allow you to actually, A, have confidence that you know the material because you were able to take a lesson at one time and then recall it later on, but then also it'll keep your foundation solid so that when we get to module 12 in the course, when we actually start writing a really big project, you will know all of the information in the modules and not have to go and look back at every module every time we go to use the heap or go to use a structure. So again, take this course slowly, do 1 or 2 sections a week, and then later on in that week, make sure you're writing code to confirm in your head that you actually know the information. So that's it for this one. We'll see you in the next lesson. Keep going. Hey guys, welcome back to another episode of Low-Level Academy. Today we're talking about the tools we're going to use in this course and how to get those tools all set up before we get moving and actually starting to write some code. So here I am in an Ubuntu 2204 long-term support VM. And we're going to use the kind of the default setup and kind of show you how to go from the default setup to a place where you can start writing and editing code. You'll see later on in the course that I use Vim and kind of my own personal setup. You don't have to do that if you don't want to. This, what I'm going to show you here, is the minimalist setup where you can go from a fresh Ubuntu install to a place where you're writing code nice and easy without being over inundated with tooling, right? I know a lot of people typically like to use NeoVim or Vim and kind of really spend a lot of time configuring that text editor to be the way that they want it. And that's probably a good use of your time if you're more of a senior or, a principal level dev. But for this, we're going to use a basic text editor, Sublime Text. We're going to use the basic default terminal. and do stuff in there. I think it's the best way to learn without getting kind of overwhelmed with tooling and spending too much time configuring your tooling. So to start out, all we're going to do is run sudo apt update, make sure that all of our repos are updated in apt. Apt, if you don't know, is a package manager in Ubuntu that allows you to install things from the Ubuntu package repo, and that's what's happening here. It's updating all the repos. And then from there, we'll do sudo apt install, do gcc, and build essential. This is just going to make sure we have all the things we need on the computer to be able to build tools. So I already have this. This may prompt you to press yes, and then you press yes and go from there. And you'll know that we can run the rest of the course if when we type gcc, we get this error, and if we type ld, we get this error, and if we type make, we get this error. If all these things happen and you don't get a cannot find gcc ld whatever, then we are good to go. Next, we're going to install Sublime Text. So I'll put the link in the description for the course down at the bottom. We're going to go to the Sublime Text website. We need to install the GPG key of Sublime Text so that we can actually install packages from it. We do that by running that command there. And then from there, we have to include the package repo in our Ubuntu package repo list. And we do that by running this command here. Copy and paste, pretty straightforward. And then we have to do another sudo apt get update, or we'll just do sudo apt update because we're not using apt get, we're using apt. They're actually two separate programs. So you see here that we actually included Ubuntu's Sublime Text distro in there for apt stable. And now we can just go ahead and use apt to install Sublime Text. So sudo apt install Sublime Text. There we go. Now it's installing it. We couldn't have done that before because we didn't have this repo in our apt. Give that a second. There we go. And then to run Sublime Text, we would do subl, S-U-B-L. And there you go. From there, now we have a fresh install with Sublime. We can kind of blow this up a little bit and we can start to type a little bit of code that we'll do later on in the future. So again, if you want to configure your environment to do more, to have more stuff, if you're more comfortable with Vim or maybe NeoVim or Atom or whatever, feel free to do that. This is just what I recommend for people that are learning to code because I think Vim is complicated for people that are learning to code fresh. So, you have to learn all the keystrokes and it gets very complicated to use Vim. So I'd like to have a simple terminal with basic tools, and then you have Sublime Text over here where you can write your code, and then you can go from there. So there you go. Continue to customize if you'd like to, and we'll see you in the next lesson. See you there. Okay, so here we go. This is the fun part of the course that we will have access to after module 12. The beginning 11 modules are kind of like an intro to the C language with examples to write as we go along. But then module 12 is where we actually start to take all of those, add them together, and build our final project. So this is a project that we're building towards. And as you're going through the lessons, figure out how you think each of the things that you're learning, like structures, pointers, the heap, could fit into this project. And obviously I'll explain it to you when we get there, but it's good to get your mind primed for that. So this is the Zero to Hero database project. A simple idea, but it'll actually flex a lot of the muscles of the C language to make this possible. We're going to create an employee database that will take a file that is a database structure and allow us to add, update, store, and search. So add, update, store, and search employee information. And the information is going to be an employee structure that is the name of the employee, their address, their hours worked, and maybe we can write it so that we can add additional information to that structure as our project grows. So we'll take a database file that we'll write, we'll come up with the spec for that file, we'll be able to add employees to that file, search through them, update them, do all this stuff, and then write that file to a disk. All of that's going to come together at the end of the course, so make sure you're thinking about how we can incorporate features in the C language to this database project. So we have come to the end of a section. So your homework for the end of the section for this week is to start thinking, how would you design an employee database? What would the different modules of the database be? And how would you use the features of the C language as you know them to design this system? And again, as we go through the course, maybe your assumptions will change, but thinking about that now ahead of time gets your mind ready for the rest of the course. So start thinking about that, and we'll see you in module 2. Hey guys, what is up? Welcome back to another lesson in Low-Level Academy Zero to Hero C programming. Today we're talking about what is the C programming language. It's probably good to understand a little bit about the history of the language and where it came from and where it is today and how we got here. So C is a general purpose programming language created by Dennis Ritchie at AT&T Bell Labs in 1972, meaning yes, the C programming language is over 50 years old. Now, while it's regarded today as a low-level language, it was actually thought of as a high-level language back in the time that it was created because it replaced a lot of the languages that were closer to the hardware and gave you a clean abstraction away from the CPU. Now, C was born out of two languages that were invented at Bell Labs, the first being ALGOL, or ALGOL, and the second being BCPL. ALGOL invented in 1960, and then BCPL in 1967. Because ALGOL started with A and BCPL started with B, Dennis Ritchie decided, yep, this language will be called the next letter in the alphabet, and hence we get C. Now, since 1972, there have been various forms of the C language, various standards that have come up through discussions amongst the C programming community. So originally, when C was released in 1972, the syntax and the formatting for a lot of things like function calls and variable declaration was different than modern C now. So first in 1972, we had the base C language, and then in 1978, we had what is called KNRC, another form of C. 11 years later, in 1989, what is known as ANSI C came out, and then 1 year later in 1990, C received an ISO certification. That's the International Standards Organization, and that helped create what is known today as C89 or C90. They both refer to the same language. Now, ISO standardization gave some general formatting changes to the language that made the language more scalable and accessible to a larger group of people. Now, since then, over the years, there have been incremental changes to the language that add certain features here and add different variable types there, but generally, C89 is known as the most standard form of C. Now, despite being 50 years old, the C programming language is still used literally everywhere in the world. The main reason that C survived this long is the amount of power that the C programming language gives you to do things on the computer. C gives you a ton of tools to give you control over the memory space of your program, to give you control flow that allows you to control how the program behaves based off of that memory, and access to the kernel API for the operating system that you're using. With all these tools together, you can make the C program do literally whatever you want. What are the pros and cons of learning C? Now, whether you're a first-time programmer, this is a first language that you're learning, or you've been learning to program for over a decade, there is significant value in learning C. But the C language does have some rough edges that make it difficult to learn if you're only used to languages like JavaScript or Python. C gives you the ability to do whatever you want. You get significant power when you write code in C. By writing in C, you create code that is human readable that gets translated directly down to machine code, and because of that, you have a lot of access to do kind of whatever you want. But with great power comes great responsibility, and learning to code in C will teach you that extremely quickly. If you make a mess, like you allocate from the heap, you have to clean it up, you have to free it. If you create a buffer for data to go into, you are responsible for making sure that that buffer is the correct size. No one is going to check that for you. When you go to put data in there, no one is going to check for you to make sure that that buffer is the right size. That's on you to figure that out. The C language doesn't have a garbage collector, which means that as you write code that uses the heap, if you don't free it yourself, your program will leak memory over time. Now, while it may be difficult and there are some rough edges that you will hit along the way, learning C will teach you how computers work at an extremely low level. And learning to code in C will actually make other languages easier for you to learn because you'll know under the hood what's going on. Learning to code in C will prepare you to learn other languages that are a little simpler, like Python and JavaScript. So that's the C language at a high level. Go ahead and watch the next video. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C Programmer on Low Level Academy. Today we're talking about what is C compared to other languages. What makes C different than the rest of the landscape, and why would you choose C over these languages? Now, C is a really, really unique language in that when you write C code, you are writing human readable language that gets translated down directly to machine code. There's almost no middleware that gets injected. Over time, you'll actually get a sense of what blocks in C convert to what blocks in assembly. It is that direct of a translation. There's almost no middleware going on and no work being done by the compiler to make your code different. Now, there are some optimizations that happen, but overall, you are literally directly writing human code that goes into machine code. Now, when discussing programming languages, we typically talk about languages in the form of the following distinctions. Is this a compiled language or an interpreted language? Does this language have a garbage collector? Is the language strongly or weakly typed? And is the language memory safe? Now, C is a compiled language, which means that when you write this code, it gets compiled down to the machine code of the architecture that you're on. So when you write C code and you use the GCC compiler, you are turning your human readable source code into Intel opcodes that tell your processor what to do. And maybe if you're on an ARM device or you're on a MIPS device, it'll change depending on the architecture, but the code becomes the language of the computer. There's no middle layer that has to interpret it. You're literally telling the CPU exactly what to do. Because the language gets compiled down to machine code, it is typically regarded as fast compared to other languages like Java and Python that are interpreted language. Python, for example, is an interpreted scripting language where an interpreter at runtime reads your code and converts that to bytecode that gets ran by the interpreter. The interpreter itself is written in machine code that runs on the CPU, but your code actually never touches the CPU. It's getting interpreted by something else. C, being compiled, does not do that. It runs directly on the CPU. And similarly, Java is run in the Java virtual machine, meaning that an interpreter turns your Java class files into JVM bytecode, and that bytecode gets ran by a virtual machine that runs on top of your CPU. So the JVM is written in machine code, but your code is only ever put into bytecode. Okay, next, are we talking about a strongly or a weakly typed language? The topic of if C is strongly or weakly typed is kind of a holy war. There's really no official answer. I will fall back to what Dennis Ritchie said in that C is a loosely typed language or a weakly typed language for the following reason. A strongly typed language is a language that demands types at compile time and enforces those types as the program runs. And a weakly typed language is a language where you have a variable and its type can change over time. So for example, in Python here, I have variable x. X is set to 4, so its type is an integer. But then I can later on in the code say that x is a string. The reason why Dennis Ritchie said that C is a loosely typed language is because while the types are strong and defined at compile time, you can, as the program goes on, change how the compiler or how the program looks at those types. You can say that X is now going to be a void star, or X is now an int star, even though it started as a float, for example, right? So because we're able to make those distinctions at compile time, the argument was made that it is a loosely typed language and that types don't survive long as the program runs, therefore making it a weaker language on the typing side compared to languages like Rust. Next, does C have a garbage collector? No, C does not have a garbage collector. Now, there's kind of a pro and a con for this. So the pro of C not having a garbage collector is that it does not suffer from the overhead of running a garbage collector. Languages like Go that use a garbage collector do have performance overhead in tracking which memory is currently in use, which memory has gone out of scope with no tracks on it, and then having to run the garbage collection run to pull that memory back into the allocatable space. Now, the downfall of C not having a garbage collector, obviously, is that now the programmer is responsible for tracking which memory is and is not in use and freeing it as appropriate. If you fail to free your memory over time, your memory will be leaked out of the program and you could eventually exhaust the resources of the system, which is not good. And finally, is C memory safe? No. You will very quickly realize that C is not a memory safe language. What does it mean to be memory safe? So a memory safe language is a language that gives the programmer the ability to write code freely and not violate the bounds of the memory that they're given. So for example, if you have a buffer of memory in Rust, a memory safe language, if I try to index outside of that array, if I try to access memory that was not allocated to me, the Rust runtime will actually yell at me and say, hey, you can't do that. In C, as I'm sure a lot of you will figure out if you're new to programming, this is not the case. C will very easily let you access literally wherever you want if you make a simple logic error like an integer overflow or underflow when indexing into an array, for example. And again, if that's confusing to you, that's okay. We will get into that into a future video. And there we go. That's pretty much how C is different than other languages. So let's take it to the next level and see you in the next video. Hey guys, what is up? Welcome back to your next lesson in 0 to Hero C programming on Low Level Academy. Today we're talking about, is C still relevant? Like, should you be learning the C language? And obviously you're here, so you probably already have your opinion. But I think it's important to talk about because there are so many new languages that come out every day. There are so many new languages that come out all the time. And new programmers want to figure out, I only have so much time. You're probably a student either learning computer science or maybe even learning a different discipline, but you want to spend your extra free time to become a better programmer. And what language should you invest your time in? So is C worth my time? And to even exacerbate that, C is a 50-year-old language. So is it too old? Is C dead? Is there something else we should learn instead? Should I study one of the big ones like Rust? I hear all the time about how Rust is the future and Rust is memory safe. Or Go. Go has a garbage collector and is really easy to write good, clean code. Those are really good examples of new languages, but I want to emphasize the fact that while C is 50 years old, literally the entire world still runs on C. There is C in your operating system right now. There is C in the browser that you're watching this video on. There is C in the router at your house. There's C probably in your microwave. There's C literally all over the world. So while the C language is extremely old, The reason that C has stood the test of time is because of the power that it gives the developer. C allows you to literally do whatever you want, whenever you want. And while that has created some security vulnerabilities in certain stacks of software, looking at you, Microsoft, it has enabled the programmers over time to write code that survived the test of time and made it into basically every device we use today. This doesn't mean that things aren't changing, right? It is true that Rust is becoming more and more popular. Go is becoming more and more popular. So if you have additional free time, I would say learn those languages as well, because you don't want to be stuck in the past and only be a one-trick pony. But you want to have your foundation set and use C for two things. A, to stay relevant and be able to program against a language that is used literally everywhere. And then also, you want to use C to teach yourself how computers work so you can take that knowledge and then go use it to learn a different language like Rust or Go. Also, a little fun fact, don't forget, things like COBOL, for example, a language that's used to program mainframes, still exist. And as the number of people who know how COBOL works goes down, the salary for those jobs goes up as well. For example, I think a COBOL engineer, if you work for the state of New Jersey, the government, they will pay you like $150,000 to go work for them because no one else knows how the language works. So there is some value also in knowing older languages as well. Now, C isn't that old. C is not COBOL level old. C is extremely relevant still, but I think it's an interesting analogy when you look at languages that are, supposedly dead, right? So with that said, let's move on to the next lesson, and we'll see you guys there. Hey guys, what is up? Welcome back. Welcome to your next lesson in Low Level Academy, Zero to Hero C Programmer. Today we're talking about variables and variables in the C language. Now, again, as we're taking this course, remember that we're trying to figure out how all these different parts apply to our person database project, the course project for this course. A variable in C is just a location where you put some kind of memory, right? You have some information that you want to use in your program. All a programming language does is store information and then do things with that information based on the values of that information. And where do we put this information? We put it in variables. So for example, if we are creating our personnel database and we wanted to store, for example, the ID, the number of a person, we would store that person's number in a variable. So to begin, the way you declare a variable in C, this is the generic format of how a variable declaration is written in C. So the part will be first the type of the variable, then the name of the variable, and then the equal sign, and then its initial value. This is going to be the way that we set up every variable declaration in the C language. This type will depend on the type of information that we want to supply to the variable. This name will be used to describe to us, the programmers, and also future programmers who may take on our work, what the point of that variable is, right? Why did we decide to make this variable? And then the initial value, right? This initial value can be a constant value, like a number like 5. It can be a string like my name, low level learning, or it can be an expression that uses other variables. Let's try a couple examples to figure out what we're talking about here. So one type that we can use to get you familiar with the C language is the integer type. An integer is used to store a number. The int type will be used like this, int, and you can see that my syntax highlighter here knows that int is a valid type, and I'm using nvim in case you were curious. Other things like Sublime or VS Code will also highlight the proper syntax. So it knows that int is a variable type in C. Now I'm going to say that my name for my variable is person ID, right? I need to have a descriptive name for the variable so that when I read this code later, I know what it does. I could name the variable P, or I could name it I, but making a descriptive variable name like person ID tells me what's going on in the code. And person ID is going to be set to an initial value of 0. I can also later make another variable called person2ID and say that its initial value is equal to, gonna move my fat head here, person ID plus 1. I can use an expression here to define another value that gets calculated at runtime. We also have other data types we'll talk about later on in different videos that can store different kinds of information, like a character, for example, that can store string information. We also have things like floats that store decimal values, and a bunch of others we'll cover later on in other videos. So guys, this is it. This is how we store variables in C. Continue on to the next video and figure out how we can use them. Continue on to the next video to figure out more about scope rules in C. Hey guys, what is up? Welcome back to your next lesson in Low-Level Academy 0 to Hero C programming. Today we're talking about variable scope rules. We're going to talk about what variable scope actually means, the different levels of variable scope, and how that will affect your programs as you write them in the future. So variable scope is basically a definition of who is able to access variables you've defined, or where in your code you're able to access them. So for example, let's say we wrote our code here and we use the person ID variable. And later on, I want to actually update the person ID variable. I can say person ID plus equals 1. Well, there are a couple places in our code that we can do this and a couple places where we can't do this. Now, the location that we're able to run person ID plus equals 1 is a place where person ID is called in scope, meaning we're able to access that variable. Now, person ID is in scope here because we are in the same function that person ID was defined. Because it was defined in the same function, person ID is known to be within what's called local scope, meaning it is locally available to us. We can update it and do whatever we want to it. There is also another scope called global scope, where if I make a variable that is outside of these parentheses, that means that they are outside of the scope of a function, that means they're in what's called global scope, meaning that any other function has access to them. So I can make a variable called integer g is what we want to tag our variable name with, g for global, and we'll say num persons. This can maybe be a variable to declare how many persons that we've tracked so far in our system. Generally, we want to actually avoid variables that are in global scope for the following reason. It's very hard to keep track of where in our code we use global scope variables. Let's say, for example, we have one function that adds the number of persons and another function that takes away from the number of persons. If we do this too many times in a certain order and lose track in our code of where this happens, it's very easy for this to run away and possibly cause logic issues in our code. It's more safe to keep variables in local scope. An important thing to be aware of when it comes to variable scope is that variables can have the same name if they are within different scopes. For example, my main function, person ID, can exist in the main function, right? We have a function called main, and person ID exists within this local scope. If I go to update person ID, I'm only going to update this variable here. The other person ID that exists in some other function's local scope will not be updated by this update. Also, we can define additional subscopes in a function by using additional parentheses. For example, if I use these parentheses here, I can create another subscoped copy of person ID, and I can make it have a different value. And whenever I update this person ID, it'll update the variable at the lowest scope, not the one that's up here. Again, these aren't super applicable right now to our project, but it's really important to know when you create variables, where you're able to access variables, and what is generally accepted as safe and not safe when it comes to global scope variables. In a future course that we do multi-threaded programming, you will see why global scope variables create problems, but don't worry about that for right now. So that's generally how scope works. Move on to the next lesson where we talk about the C preprocessor. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in 0 to Hero C programming. Today we're talking about something that I think gets a lot less attention than it should for new programmers. We're talking about the C preprocessor. The preprocessor is all of these things here that start with the pound sign, and I think typically new programmers kind of ignore it and don't really understand how it works until much later on in their programming career. But I think learning it early actually allows you to write code that not only looks better, but is easier to debug. You can add cool features to your code that makes it easier to understand what's going on and to control your code at a higher level. So let's talk about first what goes on when our compiler actually converts our human readable source code, all of this stuff, into code that gets ran by the computer. This is called the compilation process, and it happens in 4 steps. But the very first step that actually goes on before anything else happens is the preprocessor gets ran on your code. And what the preprocessor actually does is it takes these directives and copy and paste whatever is meant to happen in this directive into your code. So for example, the pound include directive literally reaches out to the global standard IO header file and copy and paste that into your code. What that allows us to do is access functions that we didn't write, like printf or scanf or puts, other functions in the standard glibc runtime that we didn't create. That's what pound include does. And then pound define is another cool preprocessor directive that allows us to create variables that act as constants where we can control how our function behaves through these variables at compile time. For example, if we have a structure of the number of people we want to have in our database, we can make a max persons pound define that we can actually access from the compiler at compile time. We can change that when we compile our code and make it do things based on what we need it to do in the compiler. We also have things like pound define debug, where we can later check if this thing is defined, output some code. Otherwise, if this isn't defined, this code won't happen. By having these really cool compile time variables, we can insert things into our code like we are in debug mode, and then use another preprocessor macro like file in line to tell us what line our code is running on. So if we have a crash later on in our code, we know about what line that crash occurred on. So the preprocessor gives us a lot of really high level power to create code that is easy to read, but also is controllable so that we can make major changes to our code with not a lot of changes to the actual lines of code themselves. Like for example, here I can go and I can compile this piece of code, and because I have pound debug enabled, I can run this code and it tells us we're on variables.c line 10, but if I disable the debug flag, that line of code goes away. And I can also from GCC define debug, and I get that piece of code back. So making our code written this way with preprocessor allows us to have a lot of really finite power over our code. So guys, that's it for now. Move on to the next lesson where you'll finally write your own code and compile it and run it on the command line. We'll see you there. Guys, what is up? Welcome back to Low Level Academy, Zero to Hero C Programming. Today, I'm very excited. Today is a lesson where you are going to open up your editor and write your first piece of code. You are going to compile it and you're going to watch it run, and you are going to feel the sensation of you have made the computer do what you want it to do. It's very exciting. We're going to assemble all the knowledge that we have so far, and we are going to have you write a piece of code. But first, I'm going to explain what's going on here, and I want to see if you can predict what's happening before I say it based on what we've learned in the previous lessons. So here we are invoking what is called the preprocessor. The preprocessor is giving us access to standard io.h. That is putting a header file into our code that gives us the definition of functions like printf, for example, that we are using in our code, but we did not write them. It gives us access to these functions. We are declaring a function called main. The main function returns an int, and again, we'll get into functions, how to make our own functions, and function declarations later on in the lesson. But this is the one function that all C programs need to have. The compiler and eventually the linker, two separate parts of the compilation process, look for the symbol called main and run that symbol first once the program is started. Within this function, within the scope of main, we have run a function called printf that prints a format string. The format string will say hello world exclamation point, and then the special character here that is called a new line that represents the enter key being pressed on our keyboard. And then because the main function returns an integer type, we are going to tell it to return 0, which is the global nothing went wrong value. So we're going to write that. And the way we're going to compile that is we are going to invoke the tool that I had you install in the first couple of lessons. We are going to run gcc, which is the GNU C compiler. We're going to say tac-o, which means I want you to output a file named. We're going to call it hello. And then you're going to type the name of your C file. So mine is called variables.c because we're kind of in the variables section right now. And if you hit enter, you should get no errors. And if we type file hello, we will see that our output file for me is an ELF 64-bit least significant bit shared object. It just means that it's a position independent executable, but we'll get to that later. But what we can do to run our hello file is we /hello, and then boom, hello world. Please take the code, write it yourself, get your fingers dirty, and run this piece of code and feel the sensation of you took human words and you commanded a computer to do a certain thing. I think doing that gives you the understanding of why programming is so cool to so many people. And yeah, so I hope you're enjoying the course so far. Please continue on to the next lesson, and we'll see you there. Take care. Hey guys, what is up? Welcome back to Low Level Academy, Zero to Hero C Programming. Today we're talking about the array structure in C. In the previous lesson, we talked about variables, right? And just to recall, a variable is a place where your memory goes. It's pretty straightforward. So if I have int id equals 0, that allocates a little space of memory that is the size of an integer, so 4 bytes. Its name is id, and its value is 0. And an issue kind of comes up if I want to have multiple variables of the same type. I could say int id equals 0. I could say int id1 equals 0. I can say int id2 equals 0. And I can even get really fancy where I can say int id3, id4 equals 0. And I can write that all in the same line. And this is actually all valid C. But the problem is you start to incur this thing called technical debt, which is this idea that updating your code and maintaining your code and kind of making it do what you want to do is a lot more complicated than it has to be. What if you wanted to just have a bunch of integers that represented the same type of data, but there was just a bunch of them? And that's where arrays come into play. So an array is literally just a block of memory that contains a bunch of the same type of variable. That's it. It's no more complicated than that. You do have to make them the same type. You cannot have an array of different types. That's actually what a structure is called, and we'll work on that in a future section. But for now, let's say, for example, we wanted to have an array. An array is created by saying the type and then the name, so I'll call it IDs, plural, because it's going to have multiple things, and then a left and a right bracket. It's called a hard bracket. This denotes an array. Inside that array bracket, we have to denote the number of elements that are in that array. And typically, it's good practice to pound define a variable. We'll call it max IDs, like the maximum number of IDs there are, and we'll put a number in there. We'll say 32. And now I will type the max IDs value inside our array brackets. So this tells the compiler that we want to create an array of 32 elements. The elements are all of int size, so 4 bytes, and its name is ID. Another way we could have made this, and we'll comment this out so we don't get an error for duplicate effort, is that we could have said int IDs without a number inside of them, and we can let the compiler infer how many we want by declaring them at start. So we could say int IDs equals, now we use a curly bracket here, note the difference, we have a hard bracket here and a curly bracket there, and we can say 1, 2, 3. What that will do is that we'll create an array of multiple objects, of multiple ints. By default, it'll make room for 3 of them, and its values will be 1, 2, and 3. So you're probably curious now, if we have this array, and I'm going to uncomment this, we can use this one with the better syntax. We'll say that for right now, the default value in our array is 0, 1, 2, and we'll assume the rest get zeroed out. That's a bad assumption, but we'll get to that in the more advanced sections for the course. Now, if we have this array, how do we use it? How do we get stuff in and out of it? Well, to access a value that is in an array, all we have to do is type the name of the array and then the index that we want to get out of the array. So for example, if I wanted to get the 0th element, which is the first element, that's kind of a new thing for some people, indexes are starting at 0. So if I want to get the first element, I actually get the 0th element. And there's actually a pretty cool reason for that. We'll talk about that in a future section. But I say IDs of 0. That will get me the first element in this array, which is going to be the 0 number. We can prove that by doing a call to printf. We haven't talked about function calls yet, but just follow along with me. Do printf %d, which prints out a decimal number, then do /n, and then IDs of 0. This is telling us basically we want to print out a format string. The format string is going to print out a decimal, and what is that decimal? It's the element that is in the IDs array. It is the 0th element, so that'll be the number 0. We'll save that. We'll do gcc taco array.c, and we'll run that, and we get 0. And we can do the exact same thing again. We can do IDs of 2, for example. So we're going to get the 0, 1, 2, the second element. It's going to be the number 2. Right? Go ahead and compile that again. We'll do array, and we get the number 2. Pretty friggin' easy. How do we assign values after it's been created, for example, right? We say IDs. Is my fat head blocking the video again? No, we're good. We say that IDs of some element. We could say that IDs of 3 is equal to, say, hex 41. We can also do the hex type here. And we can do the exact same thing. We can print out %d/n, IDs of 3. Go ahead and compile this and run it, and we get 65, which is the decimal value of hex 41. So don't get too confused by that. It's just the comparison or the conversion between hex and decimal. So that is how you do arrays at a very basic level. Again, thinking about how arrays will apply to your database project, right? Instead of having a bunch of IDs for people that are separate variables and a bunch of strings for people and stuff, instead of that, we can use the arrays to make our database essentially just an array of people structures, right? We'll get deeper into that as we go into the future sections where we actually create these structures and begin to build out the database. But this is how you use data types that are repeated contiguous memory of the same type. That's called an array. And this is the syntax of how you do basic stuff with arrays. So keep going. In the next lesson, we'll talk about strings and how effectively a string is just a fancy array. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C Programming, Low Level Academy. Today we're talking about strings, and we just got done talking about arrays, and there's a really good reason why these two lessons are together. Again, an array is just a block of memory where the type of the memory describes how big each element in that array is. So here, for example, we have an integer array whose name is IDs. It is 32 elements in size, and it's defined as 0, 1, 2 are the first 3 elements, and the other ones are undefined at this time. The reason why I want to talk about strings in this lesson is because typically, the first thing that we write in code is hello world, right? We say hello world, and we kind of just print it, and we're good to go. And we don't really know what's going on under the hood here. Strings are denoted by these two quotes here, right? We have two separate quotes that denote that this is a string on the inside. What a string actually is under the hood is just an array of characters. It's really cool because you can make your own custom string like this. We'll say char meister, and we're not going to make a pointer like you see in a lot of other programs. We're going to make an array of characters and say it's equal to HELLO, and I'll close it off. And I want to make sure my fat head isn't blocking the code this time because I already recorded this and I was blocking it and I was like this big. Anyway, so we're going to go ahead and instead of printing f that, we're going to printf a %string, and it's going to be my stir. Okay, so let's go ahead and print that out. And we're going to head, and there you go. So we can literally make our own strings like this. Now, there's no good reason to do that, right? Obviously, you can just make your own string like this. We can say char my other stir equals hello, and this does the same thing, and it's a lot less gross than this. I just wanted to drive home the point that a string in C is literally just an array of characters. Pretty cool. There is one issue with this, though. You're probably wondering, how did the computer know to stop printing? How did it know to just only give me this data and then stop giving me other data? Well, we actually have a small vulnerability here where you have to have a 0 at the end of your string. Strings in C are what is called null terminated or 0 delimited, which essentially means that it's going to print every character that it has. It'll print H, then E, then L, then L, then O, and it'll stop when it gets to a 0. If we didn't have this 0 here, for example, and maybe there was additional data at the end of the 0 that at the end of the O that wasn't a 0, the program would actually continue to print and leak to us information about the program. It literally would just give us data that's on the stack of the program where the memory is and show it to us, even though we're probably not supposed to see a lot of it. It could reveal memory about how the program is protecting itself. It could allow us to hack the program. It's very important to make sure that your strings are null terminated. And you're probably asking, why aren't we doing this here? It's because when you put a string in double quotes like this, as opposed to single quotes and making your own array, the compiler knows by default to null terminate this. It's a thing that it does on its own automatically, so you don't have to worry about it. Now, I know this lesson is called string operations. There are a few operations that we're able to do on strings that behave this exact way. They do the operation until it reaches the null byte. So these functions are things like stir copy that put data into a destination location from a source location, it'll literally just run the copy operation until it encounters a null byte. There are things like stir and copy, which take into a destination a string from a location that is up to n bytes long. And there's a bunch of other string operations we'll talk about later on in the rest of this lesson and the rest of the course. I can't talk about these too much just because these are all pointers and we have not talked about pointers yet. So when we get to pointers, we'll get a lot deeper into the string operations. But I wanted to just drive home the point that if you are having a hard time understanding arrays, if you think about a string as just a block of contiguous memory of the same type, you're literally describing what an array is. So they are basically the same, just this one is an integer array, this one is 4 characters. So in the next set of lessons, we're going to actually start doing stuff with our data. We'll go into control flow for our program, how to make for loops, how to make while loops, how to check if one value is greater than another so we can actually start having our program make things happen. So we'll see you guys there. We'll see you in the next lesson. Take care. Hey guys, what is up? Welcome back to your next lesson in 0 to Hero C programming on Low-Level Academy. Today we're talking about, finally, I think what is the fun part of programming for people learning to code is conditional statements. The reason for that is because so far the code has been kind of boring, right? We're like, okay, cool, int I equals 0, and we make some variables and maybe we print hello world or whatever. But this doesn't, who cares, right? This doesn't do anything. We can't make this code sexy because there's no logic happening. And what are computers meant to do? They're meant to process logic. So today we're talking about conditional statements. What is a conditional statement? Well, let's first have the program declare a temperature variable, and we're just going to have it read from the user that value. Again, don't worry about the syntax for this. You will understand this when we get to pointers, but just copy this out of the area below where I have the code prepped for you. And this is going to read from the user a number that is a temperature. And now I want you to print if the temperature is above 70 degrees, it's hot. If it's below 70 degrees, but above 30 degrees, it's mild. And if it's below 30 degrees, it's cold. Now, the way that we have to do this is through conditional statements. They're called if statements is the first one. And an if statement is just like it sounds. We have the if statement, we have the condition, and then if the thing that we ask about inside of these parentheses is true, then we run the code in these brackets. So we can start and say if the temperature is greater or equal to 70 degrees. And we're going to say, dang, brother, it's hot. And there we go. Pretty straightforward. Well, now, like I said, we want to check a second condition. Now, there's two ways we could do this. We could type the if statement here and say if temperature is greater than or equal to 30 degrees, and, this is an and statement, temperature is less than 70 degrees, we can say printf, dang, brother, it's mild, right? Now, there is actually a different way we could do this. This condition is going to get checked. It's going to check if temperature is greater than or equal to 70. It's going to run the check every time. And then whether or not it runs that check, it will also run this check, right? These checks are both going to get ran every time. They are independent of each other. Instead of this, because these are exclusive clauses, right? It cannot be that the temperature is greater than or equal to 70 and also less than 70. So what we're going to do is instead of saying two separate ifs, we're going to say else if. What this means is we run this if, and then we only check this clause if this one does not fail. If this one passes and we get to this condition running, we don't even care about the rest of the code. The code does not run. We do not even try to do this, right? So essentially, two ifs together are separate. They are exclusive. And then an else if means that this one depends on this one failing. And then finally, we can just say else at the end, right? And we could say that printf, dang, brother, it's cold. Sag, I live in Idaho, right? We're going to return here at the end. This is happening like this, the else statement, because there is no other condition to satisfy other than the temperature being less than 30. You know, obviously it could be like 100 or whatever, but that's handled up here, and it could be in this band, so it's handled in here. So this final case is us handling if it's less than 30, right? So this is a conditional statement where we do some logic, and then this conditional statement depends on this one not passing, and then this one finally depends on if these two have not passed, it just defaults to doing this final third thing, which based on how we designed our program will only happen if it's under 30 degrees. Let's go ahead and test this out. Oh yeah, we don't want the new line here. Sorry, delete the new line. Again, all programmers make mistakes. Don't worry about it. Just %d, no new line. And we're also going to print, you know, we want to tell the user what to do. What temperature is it? Question mark. And we'll do that. And we'll quit this. And we'll go like that. And we'll do, what temperature is it? 76. Dang, brother, it's hot. What about 55? Dang, brother, it's mild. And what if it's -1? It's cold. Cool. So those are conditional statements. Essentially, we are using the if statement to make parts of our code run based on certain conditions and other parts of our code run based on other conditions. And then finally, we have this else statement that says if none of those conditions have passed, don't do those, do this instead. Now, as it applies to our database project, when we get into building our menu, right, if the user provides an option to do a thing, you know, if menu option equals add or edit a employee, you know, we'll do a particular function here. Otherwise, if the option menu maybe was to delete an employee, we do a function here. These are the building blocks of coding that we will use in the last module to go through and build our big project. So please take some time, really write some code, understand this, and we'll move on to additional control structures and control flow structures later on in the lessons. We'll see you there. Hey guys, welcome back to your next lesson in Zero to Hero C Programming, Low Level Academy. I've been saying that a lot. It feels good to be saying that because I'm happy you guys are here learning with me. So again, like I said in the pacing section of the course where I really want you to take time and sit back and absorb this material, the reason I said that is because the material is going to ramp up in quantity a lot as we go through these next couple of lessons. The content gets a lot more dense, and I want to make sure you guys really fundamentally understand this stuff before you go and try to apply it to, you know, building significantly sized projects, especially for people that are new at programming, right? So if you feel like you're comfortable and you're actually getting the material, then good, please keep going. If not, please take a step back, go watch the material again, make sure you really understand it, then keep going. Okay, so in our previous lesson, we went through and I talked to you about how to do conditional statements, right? So we have int ID equals 1, you know, maybe this is a user input generated thing, and we say if ID is less than 0, or if it's greater than 0, we'll do something fun, do something neat, right? This is just us checking the input and seeing if it meets one of our logic constraints, and if it does, we do a thing. Awesome, pretty straightforward. So what if we wanted to do multiple things over and over and over again, right? We can use the array case for an example to kind of drive home why this is so hard. Int IDs of max IDs equals, we'll put 0 here. What this does actually just initializes our entire array to be 0. And we'll do, again, pound define max IDs to be 32. Now, what if I prompted you? What if I told you that our requirement was to have every IDs of, so IDs of 0, equal that value, right? If I wanted to have IDs of 1 equal 1, right? Again, this is arbitrary, but it drives home the point that we're going to start finding ourselves repeating ourselves very, very often. This is going to get very annoying and complicated to deal with. So what we can do instead of doing this really gross looking horribleness that I never want to see again is do what is called a loop. So a loop is literally what it sounds like. Picture a circle, right? It just goes around in a circle, it keeps going. A loop, it just means do the same thing over and over until some condition is met. That's all a loop is. And in C, we actually have two, technically three ways of doing this. We have for loops, we have while loops, and we have do while loops, which is like, it's like a while loop, but it has like a special condition. We'll talk about that right now. So a for loop is a special kind of loop where the syntax is like this. Typically, we create what is called an iterator. The iterator is noted by the letter I, right? Typically, if you say, you see for I equals, the reason to use the letter I is because I stands for iterator, because we are iterating over something. Now, what the for loop is going to do is it's going to have inside these parentheses, it's going to have 3 clauses. We are going to first initialize our iterator. And you're probably saying, why did we do that? We just did that up here. Well, it's bad practice to not initialize your variables, and it's not good practice. It's bad practice to initialize your iterator. So we're going to do it twice because that's the right thing to do. And then we're going to have inside of the second part here, the second semicolon buffer area, we're going to have what is called our truth clause. So the truth clause is the thing that is going to be evaluated to see if we have to run again. So if we're iterating over our entire array, we want to use I to do what's called index into the array. And we only want to do that while I is less than max IDs. Because if it gets bigger than max IDs, we're indexing out of that array, and then we're doing illegal things in C. And then finally, we have the last part of this, which is the take action clause, or the thing we do after every loop. And what we're going to do here is do I++. This is going to increment our iterator by 1. So again, the syntax is initialize your iterator. How often does this run? What has to be true for this to run? And the truth is that I is less than max IDs. And that's obviously true at the beginning, and it will continue to increment I every time until this is no longer true. And then we put the thing we want to have happen every loop, right? Because this is going to happen max IDs numbers of times. So what we're going to do is we're going to say that IDs indexed by I is equal to I. Okay, that's going to say IDs of 0 equals 0 the first time. And it's going to iterate, it's going to check, is I less than 32? Yes. So now I equals 1. IDs of 1 is equal to 1, and so on and so forth. And just to prove this, we're going to print 2 numbers. We're going to have %d colon %d. And those 2 numbers are going to be I and IDs of I. Right? We're just going to print that out every time. And don't forget your new line character here, because otherwise you get a bunch of crap that doesn't hit enter and it looks like garbage. Yes, we'll write this. There we go. So this is exactly what we thought it would do. It would do for 0 through up until 32, right? Which were less than 32, so it's actually 31. And then it set IDs of that number to that number. Let's try it again, but just to prove that it's different, let's set it equal to IDs of I equals I times I. So now we're doing some fancy like squaring, right? Okay, so 1, 2, 9, 16, right? So we're getting all the squares of these numbers. Pretty cool, right? So that's the for loop. Very straightforward. Again, initialize the iterator, the truth condition to run the for loop, and what do we do at the end of every for loop? Now the while loop is actually even simpler than the for loop. So we're going to reuse our I variable here. So I'm going to say that I equals 0 again. Now the while loop has only one condition, right? Inside this bracket, inside these parentheses is a truth statement. And all we have to do is write a thing to be true for the while loop to execute. So we'll say while I is less than max IDs. Now it is simpler than a for loop, but we are actually the ones on the hook to increment our iterator now. So we have to, at the end of every while loop, do I++. And we'll do the same thing we did before. We'll do IDs of I equals I times I. And this will have the same exact effect as this line here. And I'm going to go ahead and compile this and let you guys see it running twice. All right, so we have, ooh, did I introduce a bug? Oh yeah, dude, this is why C is so crazy. Again, we're not going to go into the details of this, but basically because I incremented my iterator before I printed, I was able to index outside of my array and reveal a number that was out of the bounds of the array. So this is actually a bug, and you have to make sure you put your iterator at the very end of your for loop. That's a fun little Easter egg for you guys. And I'm not going to cut that out. That's a cool learning experience. But I will show that the for loop is doing one thing. It's doing the same thing. It's just this is a different syntax doing the exact same functionality. And then finally, we have the do while loop. So the do while loop is basically a while loop, only it will always run one time. So we can run the exact same logic here. We'll say that I equals 0 to reset our iterator. I'm going to steal all this. I'm going to put it in here. I'm going to learn to use Vim one of these days. Okay, and we're going to say while I is less than max IDs. All right, it's going to do the exact same thing. We should see this happening 3 times. Oh, sorry, it's do thing while. I apologize. I missed that on the syntax there. Cool, so we run this, and we should say it happening 3 times. 2 and 3, there you go. Exact same functionality, just through 3 different ways of doing it. Yeah, so this is a while loop where while will check this condition, and if this condition is not true the first time, it will not run, period. Whereas this will run one time, always, and then check the condition. There are certain instances where that matters, and we'll get into that when we actually build our project. There may be a case where you want to run an area of logic and then check the condition after your logic runs, and if it's continuing to maintain a certain state, do that again. That's where do while is good. But yeah, so these are our loops. This is how loops work in C. These are the only loops that exist. I hope you take this away and pull a little bit out of this. When you are iterating over a large structure and you need to do some kind of repetitive logic over and over again, loops are super useful, and I'm sure you can see why. So that's it for right now. We're going to move on to our next lesson, which is functions. Functions are super, super important in C. It's going to really, really allow you to break your code into multiple parts that make sense, and we'll see you guys there talking about how to make our code a lot less ugly and a lot less long like this. So we'll see you in the next one. Hey guys, what is up? Welcome back to your next lesson in Zero Hero C Programmer Low-Level Academy. Today, we're talking about functions, right? What are functions? What is the syntax of functions? What is good practice for functions? All that stuff, we're talking about it today. Let's dive into it right now. So like I said on the previous lessons, right? Your main function is basically just the block of code that will run every time your program starts. The compiler expects main to exist. Now, inside of these little curly brackets, there's something I've kind of been ignoring, but it's what's called the function parameters, right? The arguments that are given to your function to make it do stuff. We're not going to talk about the arguments to main right now, just because, they're a little complicated. They have to do with command line arguments, but technically there are arguments that go to main that looks like this. If that scares you, that's okay. It scares me too. Don't worry about it. But let's talk about how we can use functions to make our code look a little cleaner, right? So how do we write our own function? What is the syntax of a function? The syntax of a function is very, very simple. So typically what we do is we say something like the return type of the function, then the name of the function, then the list of arguments, and then we define the function, right? And we go like that. So this is how every function in C is defined. And that's exactly how the main function is defined, right? We have a main function, the name is main. It returns an integer, which actually is the value that tells the computer if our program failed or not, right? And then we give the argument parameter list, the list of things that the function needs to behave, right? Our input from the user. Now you're probably asking, what does return mean, right? What does this return type have to do with anything? Well, let's say, for example, I wanted you to make a function that added 2 numbers. The result of that add function would come out of the function through the return value. So what that means is that it would give back, as a result of the function, a number, and that number would be an integer type. So let's say int add. And then the values that I want you to add together are going to be the arguments to that function. So that means that we want to give the add function 2 inputs. So it'll be integer x and integer y. And now we have to define what that function does. Add will create another variable called z, and z is going to contain x plus y, and then we're going to return z. What this means is that whoever ends up calling the add function will be presented with the result of the addition. It'll be presented with z. And again, it's important that we make sure that these types align. Int z is a type int. We're returning z. The return type is int. Everything is good. We're good to go. So let's go ahead and say that we have int other int is equal to add 1 and 2. This is how we call the function, right? We say the name of the function, then we put these little parentheses around it, and inside those parentheses, we put the numbers that we want to pass to the function. The function will then get ran right here. It'll jump up here to our function. It'll run the functionality and then return that value. And now we can do print %d, and then we'll do other int. We're just going to print out that value. And just like the add function, when we've been doing printf this whole time, kind of something I've been glossing over, we are calling the function printf, which exists in a different library. And the arguments to printf are this string that tells it what to print, and then the list of arguments like other int, the thing I want it to print, right? And then finally, we're going to be good little programmers and return 0 from main. Let's go ahead and compile that and see what we get. So gcc taco functions.c, and we should get 3. Very nice. Easy peasy. Now, that's how you use a function, but why do we use a function? I've talked a lot about this in my videos, but the high-level idea is that it's good to be lazy as a programmer. And what do I mean by that? This add is kind of a bad example, right? Because, this line is a single line of code. It does not need to be its own function. But let's say that we made another function called initialize employee, or let's make this initialize employee structure. And we'll say that the argument to this is going to be an employee pointer. And again, we haven't talked about pointers yet, but just trust me that this could be a function, right? Inside this function, we would do what the name of the function says. We're going to initialize a structure to contain employee data, right? If we are going to initialize multiple employee structures, if we're going to run that code multiple times, we are incentivized to write code one time. Do it once. We don't want to do things multiple times. Dry, DRY, don't repeat yourself. By writing a function that does something, we effectively put all the logic to perform a certain task in one place, so that instead of writing that logic over and over and over again and being bored of just writing the same code over again, we can write it one time and use it over and over again. So as we begin to develop the logic behind our employee database, a lot of that's going to be dependent on creating functions that perform singular, simple tasks. So we'll have one function that initializes the employee structure. Maybe I steal this definition and I make one that says destroy the employee structure, right? We have a single employee structure. Maybe this is the one that sets it up and mallocs it from the heap, and then we return it. And maybe this was the one that, clears all the fields and removes it from our file, right? By making a function perform one single task, a single task that you can describe in a sentence, right? Initialize structure, destroy structure. It makes the code very easy to organize and design your system in a way that you can write code cleanly. So that's it for now. That's kind of at a high level how functions work in C. I want you guys really to take this in and start to visualize based on how you saw loops working, based on how you see these functions coming together, based on generally how you do user input. How would you begin to organize a program that you need to create a bunch of data that stores employee information? This will become a lot more clear when we get to the structure part of the lesson, because that allows us to make structures that have different data types. Right now, we're kind of stuck with arrays, and arrays only have one kind of data. You can have an array of integers, you can have an array of characters, but you can't combine characters and integers in the same structure. Later on, when we get to structures, the thing that allows us to put multiple of those together, it'll start to make a lot more sense how this whole thing is going to come together and make a really, really cool project for you to play with the C language. So let's move on to the next section where we get into data types and eventually structures and start tying this all together. Let's do it. Hey guys, what's up? Welcome back to your next lesson in Zero to Hero C Programmer on Low-Level Academy. Today we're talking about a really, really important concept in C that'll begin to actually allow you to create the scaffolding of your employee database project. So previously, we had talked about these things called arrays, right? So if we had multiple IDs for multiple employees, for example, that we wanted to logically combine them, we could do it like this, but this gets very complicated and kind of annoying to manage. You know, we'd have to like manually set these each by name, and then later on in the code, we have to say like if ID2 equals some value, and then do some logic based on that. And this is very hard to grow as a code base. So you can't do anything with this without having to manually add lines of code per new ID. It's disgusting. So what you do instead, that we talked about in one of our previous lessons, is an array. So we can say int my IDs, plural, and using the square brackets, we can declare up to n, so n being 32. And again, we said max IDs, we want to create a constant, right? Reminding you of all this. Pound define max IDs is a 32 value. So we can create an array, and we can join all of those IDs together. Now, this begins to make your code a little simpler, but we don't really want to logically combine all of the IDs in our database. We want to logically combine all of the employees in our database. And the problem is, what if the employees have multiple kinds of data? What if they have a float, like a decimal income value? And what if they have maybe a name buffer where we store their first and last names? 64 characters allowed for that. A lot of issues come up where in an array, we have to combine only the same data types, but I want to join multiple data types together. This is where a structure comes in. And this is where we're going to start to define some structures that we're going to use in our project. So to create a structure, and again, a structure is a block of memory where multiple data types of different or the same types are combined together in a logical block, right? So for example, I can make a struct employee T, and we use the underscore T to denote that it's a type, and we can define that by saying employee T, and then we do curly braces, and now we can start to put in the fields of that employee T. So I can say int ID, I can allocate, let's say, first name, and I'll give him 64 characters for their first name. I can give last name 64 characters, and we can do float income, and I can say bool is manager, right? We can do all this stuff. So what we've done now is instead of having an array of all these different types together that really it's kind of clunky, we can logically combine all this information to represent a single employee. So how do we use that? Well, let's create a struct employee here in our code and kind of go through how we'd want to put this code together. So let's say we have struct employee T, call him Fred. And we could say that Fred.income equals, we'll give him, he makes $100 an hour. This guy's rolling in the dough. And also Fred.isManager is true because he's our manager. By writing our code this way using structures, we can combine this information in a way that's actually logical as a human would expect it. A human would not expect an array of IDs, an array of incomes, an array of managers. It would just expect the information to be aligned against a single person so that we can manage that single person. So combining this idea with arrays like previously, though, we can start to do really, really interesting stuff. And this is where the main part of the database is going to start to come into play. What if I wanted to have an array of employees, right? I mean, I can do an array of ints, right? I can do int my IDs. Can I not just do struct employee T employees array? And we'll say we allocate 10 employees. We can actually do exactly that. And this is almost the entirety of the employee database. Obviously, we need to write code to add and edit and take away, do it safely. But at this point, you've created a structure in memory that has room for multiple employees. And if you're able to read and write this out of a file, you've created almost the basis of storing this information about the employees, which is pretty interesting. So how do we use this? Well, let's use our for loop from the previous lessons. We'll do for I equals 0, I less than 0, or let's do I less than 10, I plus plus. Actually, no, this is bad code. What we'll do is we'll make a pound define max employees, make it like 1,000, right? Let's show that our code is saving us time, and we'll do max employees. And we're going to use that number here, max employees. And then we'll go through and we'll just initialize every employee. So it's employees of I dot income equals 0, right? Employees of I dot is manager equals false. There's lowercase f in C, right? And so we are able to now do things programmatically using the employee structure and using loops where we are able to have really, really logical control over this data using the power that C gives us. And again, talking about functions before, we would probably create this as a function like, initialize employee database, something like that. We'll get into that in module 12 when we actually begin to logically design this program. But I want you to understand how much power the struct keyword gives you in C, because it allows you to organize your data in a way that you would logically expect it, and then you can use the control flow statements in C to allow you to edit it in a way that makes sense to you. So go through, play with this, do things like print, let's do %d employees of 10, right? So get the 10th or the 11th employee, and print there, let's do income, right? And this is actually going to be a float. It's not a %d. Let's go ahead and run that real quick. GC taco struct.c. Oh, no, it's standard bool. Yeah, sorry. So to use bools, you have to use standard bool. But if we do struct here, we'll show that the income of the 11th employee, because we haven't initialized it yet, is $0 an hour. Very sad for that guy. So anyway, get into your code here, start messing around, start writing different parts of your employee structure now, start adding code where you're able to, set these values, just play around with the structure, make sure you're comfortable with it, and then understand that you can create arrays of structures to really begin to scaffold out what that database looks like. So keep going. We'll see you in the next lesson where we talk about unions, which isn't super relevant to this project here, but it's important to know what a union does. So talk about that and see you there. Bye-bye. Hey guys, what is up? Welcome back to your next lesson in 0 to Hero C programming on Low Level Academy. Today, we're talking about unions. Now, unions are not super relevant to the course project that you're going to be writing at the end of the course in module 12, but I think it is important to talk about because it's one of those things that people probably see in code as they're maybe reading other code bases and don't really know what a union does. So in a struct, for example, or a previous project or a previous lesson, a struct will allocate enough memory to contain all of these elements, right? I want to have enough room for an ID, and then 64 bytes for a first name buffer, and then 64 bytes for a character buffer, float income, etc., right? So it's going to allocate all the memory for all of these types. Now, the union type is a little weird. It's a little different. So a union will create enough room for the biggest element. You're probably kind of curious, like what purpose does that serve? So let's do my union U, just call it a union. It'll create enough room for the biggest element. So for example, if I have int x and I have char c, the union will only be int x wide, which is 4 bytes on the system that I'm using right now. The reason for the union type and why it kind of exists is if, for example, you were doing embedded stuff and you wanted to have access to all 4 bytes within the 4-byte int type and didn't want to have to do the manual math every time, what you could do is by looking at the value c, you would get access to the first byte of the 4-byte character x. I know it's not like super relevant for this project here, but just understand that a union is a type that only creates enough room for the biggest element, and you're allowed to access all the sub elements. And I can do like short s, for example, right? But let's kind of show you guys how this works. So I'll make a union, my union u, we'll just call it u. We'll say that u.x equals 41, 42, 43, 4. And what I'll do is I'll print all the different parts of it. So I can do %hx, which gives you half. And I'll give you %hhx, which gives you half of half, so a quarter. And then I'll print that and I'll give it, we'll show you the short u.s and we'll do u.c. And this will show you basically that when I'm using the union, I set the larger value. And by using u.s and u.c, I'm accessing internally the smaller parts of this bigger X. I know, super weird, super complicated. Don't worry about it for this project too much, but it's just good to be aware this is that this exists. Do gcc taco union, union.c, we'll run union. Yeah, so again, by showing you, we made the value hex 41424344. By using union.s and union.c, we got access to the internal short and the internal character of that larger int x. So keep going. Don't worry about this too much. Just understand that a union exists, and that if you're doing more complicated memory management related embedded programming, for example, you'll need to know what a union is. So keep going. We're going to talk about next special struct modifiers and how we're going to use those in our project to pack our structures super tight so that we know exactly where the memory is. We'll see you there. Guys, what is up? Welcome back to your next lesson in 0 to Hero C programming. Today we're talking about some special struct modifiers that we can add to our structures to make them a little cleaner, but more importantly, to make our code interoperable between different systems, right? So when we have a structure, we talked about this before in our last two lessons, we're creating enough memory for all of these types. Now, what that kind of implies in your head is that, oh, okay, the size of the structure is equal to the sum of all of the sizes of the parts, right? Well, that's not actually true. Depending on the system that your code gets compiled and ran on, it may add additional optimizations under the hood that add padding characters in between these fields that you're not aware of that are there. And the problem with this is that if you have two different copies of this code that gets compiled on two different systems, but you expect them to talk to each other externally, the issue is that if they're optimized for different reasons, the structure begins to look a little different, and you can't actually expect the offset to ID on one system to be the offset to ID on another system, right? So to prevent this issue, what we can do is we can add special struct modifiers onto our code to make sure that there's no additional optimizations put in between the different fields, right? To do that, we'll do attribute underscore packed. And it's actually going to be two of these, like this, and then we'll go from there, and we'll do gcc taco struct and struct. And if you ever want to test this, what you can do is actually check the size of a structure by typing the size of macro. So we'll do size of employee is %d, and we'll say size of employee t. This will get us the size in bytes of that structure. So let's do it the first time without packing the attribute to kind of show you what it might blow up to. Do this. We'll do GCC. Oh, I'm sorry, you have to do struct employee t. Size of struct employee t. Struct, so it's 140 bytes, which makes sense. 64 plus 64 plus a few others. And we'll do struct bim struct. Now we'll do attribute packed. We'll see if I actually saved any space or if I'm just made of nonsense. GC struct 140. Okay, well in this case it doesn't matter, but this will actually save you a lot of heartache in the future if you're sending this data across different systems or you want to store it into a binary structure on the disk. So with that being said, take this time, go write some code, go use some structures, and get your mind wrapped around how you can use structures in your employee database in the final module, and we'll use that there. So we'll see you in the next lesson. I'm pretty sure about pointers, and we'll see you. Let's go do it. Goodbye. Hey guys, what is up? Welcome back to your next lesson in 0 to Hero C Programmer. Today we are going to be doing a lot of stuff. We're going to be learning not only about pointers, but we're going to be taking previous lessons information like structures and functions and putting them all together and showing you how these concepts really do stack on top of each other to allow you to write really powerful code. So again, like I said in the pacing lesson, please take your time. Please spend time to absorb this information and really make sure you get it before you start stacking ideas, because if you don't and you rush, you may find yourself really starting to slip and not have a strong foundation. But if you're comfortable and you're ready to get into it, let's get into it. So I find that pointers are an idea in programming, and specifically in low-level languages like C, that really trip up new students. So I want to kind of talk about what a pointer is, why we use them, and how we use them all in this lesson. So a pointer is literally just a value that happens to be an address. That is it. And what do I say when I say address? What do I mean? So let's say, for example, I make a value called int x, and we'll say that int x equals 3. When I type this line of code, what the compiler does is it makes room on what's called the stack. It's basically just a memory location in the program that you put things that you're using at runtime, right? When I make room for x, the place that I make room for it, or the place that I put it, is the address of x. It's the place that that x lives. So if I were to make a pointer to x, all the pointer is going to be is a value that equals the address of x. So I said that out in English, right? Now let's make that happen in code. So let's say I have an int pointer, that's what the star means, in the declaration side of the expression. So on the left we have the declaration, and on the right we have the assignment. On the left, when I say int something, it's an int pointer, and it's going to be px. And this doesn't mean anything. I could literally name this potato, right? But I want to name it px because I want to show to you that it's a pointer to the x value. And then I'm going to assign it. Now, what do I assign a pointer type that I want to point to x? Well, I assign it the address of x, right? So this ampersand means the address of, and then I say the thing. So this whole line in English means create an integer pointer whose name is px, and it set its value to the address of x. That is it. That is all a pointer assignment is. Okay, so when we're talking about pointer assignment, that is the syntax. The star here means a pointer type. But when I'm going to go forward and use the pointer, I have to do a little bit different of the syntax. So let's say I wanted to use int px to get the value of x, right? If I want to use px to get x, I say the thing pointed to, that's what this means. It means to dereference, to turn a reference into a value. Dereference px, right? This literally says get the value pointed to by px. And if you're curious about what px itself equals, what did I say before? Px is literally just a value that happens to be an address. So let's print out the pointer value of px. And let's print out the value pointed to by x. Let's show you what that looks like real quick. Again, so let's look back at our code, right? Vim pointers.c. Right here, I'm getting the value pointed to by px, which is 3, right? And then let's say also I wanted to get the value of px itself. I wanted to show you that it's a pointer. Well, look at that. It's literally just a large value that is an address. Awesome. Now, a lot of people, whenever I show this example, the immediate question is, why are we even using pointers, right? Like in this case, why did you have to dereference px? Why could you not have just used x? And that's actually a really, really good question. In this case, the integer is a bad example because not only are they in the same scope, right? They are like the same size. There's no reason to pass around int pointers in this case, right? But we talked about in our previous lessons a structure. And again, this isn't the exact structure for the project, but I want to show you what we're talking about here. So we have employee t, the structure. And let's say it has an int ID, and it has an int income, and it has a bool bool staff, right? Is it a staff member or not? And we'll also have to include a standard bool for this. Cool, so we have that. And we're gonna create an array. And we're gonna create one employee t. So we'll say struct employee t, I'll call him Ralph, right? Now, in the previous lesson, what we did is we said, okay, cool, so we're gonna initialize Ralph. We'll say Ralph.id equals 1, and we'll say Ralph.income equals 0. Like we're basically setting the default value for Ralph. Well, in our functions lesson, what we talked about is if we're doing the same kind of operation logically on a thing, we want to make a function to do that thing. And we even gave the example, right? We said void initialize employee. Okay, well, if the employee is declared in this variable scope, initialize employee can't access it. So how do we make this work? This is where pointers come in. So what we're going to do here is we're going to create a variable or a function called initialize employee. It's going to take a struct employee T, we'll call it E as input, and it's a struct employee T pointer, right? It's not the structure itself, it's the address of the employee. And all this function is going to do is initialize the employee. So we're going to say E of ID equals 0. We're going to say E of income equals 0. And we're going to say E of staff equals false, right? And then we're going to return nothing because it's a void function. Void function is returned, it is return no value. And so how do we call initialize employee on Ralph? Well, this takes a struct employee T pointer. How do we get a pointer from Ralph? We just say the address of Ralph, right? So this is where he lives. This is his memory location on the stack. And then we say this is the pointer. We pass him in, we set him, and we go from there. And let's just prove that this works by printfing Ralph.income at the end of this code, right? So let's check that out. There we go. His income is 0. Very cool. So this is pointers at a high level. When you have variables that exist that are out of scope, but you want to use them in other functions that logically perform a single task, like initializing an employee or destroying an employee or something like that, you use pointers to pass around the where they live in that scope, and then have that other function now have access to that variable and do a thing on it. So we can use this kind of logical structure here to add new functions like update employee, set employee ID, update income, things like that we'll use later on in the project in the final module when we finally build the whole thing out to really make our code logical and debt-free. Let's move on to the next lesson where we talk about dynamic memory allocation, what that looks like in C and how it can kind of hurt you and how we can fix it. So let's see you guys there. Guys, what is up? Welcome back to your next lesson in 0 to Hero C programming. Today we're talking about dynamic memory allocation, what that means, how you can use it incorrectly, and how to use it correctly. So in our previous lesson, we talked a little bit about how we use structures and pointers together to create code that performs logical functions with data that may be out of scope, right? So for example, we created this employees array here, and I passed the address of the first employee to this function to initialize it, and previously we printed that data out. Now there's an issue with this code from a performance and optimization standpoint, where every time we run this code, despite the amount of employee space that we need, we are always allocating 1,000 employee structures on the stack. Now, we don't want to do that for 2 reasons. One, it limits us to the amount of employees that we can allocate. We can only ever allocate 1,000. But also B, we're kind of wasting memory here, where every time we run this program, we're blowing up the stack, and it's kind of just a waste of memory, right? So what we can do instead is we can use a memory allocator, and glibc, the libc that you use by default in GCC, has a memory allocator, and you use it in the following way. So instead of employees being an array here, we're going to now treat employees as a pointer, right? And when you do a pointer type, it may point to one element, but you actually can use this pointer to point to an infinite number of elements further out from the base element, right? So now instead of employees being an array, employees is now a pointer, and we're going to set it equal to malloc, right? So malloc is the memory allocator. We're asking libc to return to us a pointer to some amount of memory. And how much memory do we want? We want the size of struct employee T, right? That is 140 bytes, as we saw before. So we're going to ask how big a structure employee T is, times the number of employees that we want. So we could use our max employee structure here, or the max employee's value, and get 1,000 back. But what's cool about using malloc is now instead of using some gigantic constant, we can actually use a runtime value, like I say, int n equals 4, for example. We can use int n equals 4. We can use n to only allocate the amount of employees that we need. Now, it's good practice to make sure that you check that your pointer did not get null returned, because sometimes the memory allocator can fail, and if it returns null, well, then we don't want to use that memory because we can't dereference a null pointer, right? So we can say like printf the allocator failed, allocator failed, and then we return -1, which is a bad error code, right? This is us telling us that the code failed. And then otherwise, we do the exact same thing. We initialize the employee. We use, the ampersand to get the address of the employee, and we go from there. And then now, once our code is over, we need to give the memory back to the allocator, right? So when you're using code that uses dynamic memory allocation, it's really, really important to avoid what is called a memory leak, where effectively the memory in your code does not get given back to the operating system. And over time, you can actually allocate all the virtual memory allowed for your process, and the kernel will end up killing your process, and it's bad voodoo, right? So what we want to do is, once we're done using this memory, we write free employees, and this will give the employees value back to the allocator. Now, what we want to also do is make sure that we set employees equal to null, right? Because if we have this pointer and it's freed, given back to the allocator, we don't want to enable ourselves to use it, right? That's what's called a use after free. It's a huge set of bugs that create memory corruption vulnerabilities in code. So by not only freeing it and giving it back to the allocator, by effectively deleting the pointer, we remove ourselves the power of being able to accidentally use it in the future, because if we tried to access this, it would crash the program. So let's go ahead and just show you this working real quick. We're going to printf. We'll do %d. I'll do employees of 0.income. We'll do that. And we'll do a little GCC. We're going to get a bunch of warnings here because I didn't include standard lib. Let's actually go ahead and include standard lib. So as you're using new functions, by the way, in C, what you want to do is do man that function, like man malloc, and make sure you're including the header file that comes with that function, right? The C compiler knows what you're talking about and will do it for you most of the time, but it's good practice to do it yourself, so your code behaves correctly. Good, so we have that, and now we have 0 dynamically allocated, not statically allocated. That's dynamic memory allocation at a high level. Effectively, what we're able to do is, instead of depending on compile time values or values that we know in our code, we can read data off the disk. Like maybe the database header says that, we have n number of employees, we have 4 employees. So this value came from the database header, right? And now, instead of allocating 1,000, right, we can allocate a runtime value, n, and then use that later on in our code. So that's it for now. Next lesson, we're talking about static memory allocation, which is another kind of memory allocation that happens in the program in the data section. But we'll talk about that in the next video. We'll see you there.